Hi, and welcome to today's exercise on blockchain-based systems engineering. My name is Uli. So today we're going to talk a little bit about, first of all, about the next few weeks, about what's going to happen today. And then we're going to talk a little bit about the exam, what you have to watch out for, what we need to discuss. And then we're going to take a look at the solutions of sheet 8, which we introduced last week. Also very important, we do not have a new sheet today, no sheet 9. I'll come to that in a second. And afterwards, we're going to cover the last lecture of Ethereum, because we did not manage to get that in time yesterday. So this chapter 10, I think, is something that we have to cover today. But I think we covered a lot already here in the exercise. So I think we can do this rather quick, but look at it a little bit at the more interesting details so that you know what's going on here. About the exercise sheet 9, so the exercise sheet 9, I can give you a small small intro into that. Because we actually have an exercise sheet 9, but it's I can give you my Chrome here. So we have an exercise sheet 9, but it was always meant for a so to say for advanced education. So if you're interested in terms of how can I do development in blockchain and in systems engineering, and I'm more interested in that and I want to know more about that, then there is this exercise for Ethereum 4. And that's something that we can take a look at shortly. There is also a solution provided on our GitHub. You also find this in Moodle. So just go to Moodle and there's a link to this GitHub. And you can take a look at it, but it's very much focused on the question, okay, how can you really develop software? How can you use dApps to create it? So it's really an interesting exercise. It's not mandatory, and it's not there is no knowledge in there which you require for the exam, but obviously it helps. So going out there and learning things about blockchain will certainly help your performance in the exam. But it's more a development-driven task. So be aware of that. So I want to give you a little bit of sheet about a timing topic, so to say. Let's take a look at maybe the timetable here. What you see here is the PowerPoint slide that we introduced in the first exercise, so organization slide, and where we covered a lot. So we covered the cryptographic basics, all of Bitcoin, and are now here at the 1st of July with the last Ethereum exercise, so to say. And we also did not cover, unfortunately, this dApps topic, so we're going to do this today. Next week, we have 2 lectures. So this session on Wednesday is not going to be held by me. Obviously, I'm moderating it, but Professor Mattis will hold the lecture there. So we have two lectures about Hyperledger, but we don't have an exercise about that. And then we will continue with quarter 1. So quarter is another form of blockchain. The week afterwards, this exercise is going to be a guest lecture. So also, this is basically the Wednesday slot, and this is also going to be moderated by me, but I won't hold it. And then on last lecture session, so to say, we will have the guest lecture on zero knowledge proofs, and we will have on the Wednesday then the exam preparation. That's the last session I will hold, where I'm going to answer all your questions, where we talk a little bit about the exam and about the details and what's going on, because as you know, on the 27th of July, we will have the final exam. So it's a little bit on short notice, or a little bit the time frame between the last lecture or last exercise and the exam is quite short, but I don't have an influence on that, unfortunately. So we have to cope with what the faculty tells us about these exam dates. So maybe use this situation to shortly talk about the exam. So you got an update on that. I wrote several emails, I think, and what we thought of, okay, we received so many emails in terms of, okay, Uli, please can you do some online exam? And other students said, okay, Uli, please can you do some kind of, we don't want to do online because of data privacy reasons. Can we do an offline exam? And it first of all seemed very complicated to me, but fortunately, TUM exam allows us to conduct these 2 exams in parallel. Yeah, it's not super sexy for me, but it doesn't help, I think. So we will monitor obviously our offline exams in Garching, but we will also monitor our online sessions, or online exams with Zoom or a Big Blue Button. And the important part here is that we wanted to give you a equal chance as all the last years. So in terms of, we do not want to increase the difficulty, we do not want to lower it, but we want to make it more or less comparable. And therefore we have a closed book, so no additional materials are allowed. And if you have no internet connection that is viable for a video call to Germany with Big Blue Button or with Zoom, then I'm sorry, I really can't help you. The only legal allowed solution would be an open book exam. But as you can imagine, creating an open book exam for this will lead to a much, much more difficult exam, because, yeah, obviously all the contents are given, so I can just repeat, for example. So obviously that's not going to happen that easy, but for example, easy repetition or adoption of questions out of the exercise is something that you usually do not do in an open book exam. And the time is also clear, I think, right now. I'm waiting on an update. If there's any issue, you can sign up for the lecture type you want. So there's a question on TUM on Tweetback. Do we need an excuse like being abroad to take the exam online? I have an exam earlier at Arztstraße and would like not to come to Garching. Can I register for the online exam? So I won't. You can sign up for in the type of exam you want, either online or offline. You have to decide upon that, and I won't check. I don't know, 200 or 100 reasons for, or so you don't need to send me anything. Just sign up for the exam you want. It's easier for us if you go to the offline exam. It's much more convenient for us. But if you really need to do an online exam out of several reasons, then feel free to do so. And you don't have to send me anything about that. Okay. So time wasted on organizational details. Let's get a look into exercise sheet 8. We have here the exercise sheet 8. I think we can make it more fancy here. Very good. And so I think we rather go quickly through this, as it's not too much, and it's also, I think, more important the lecture, I think. Okay, let's jump into. So in the lecture you learned about the Oracle design pattern. What is an Oracle and what is it used for? So in general terms, an Oracle is a third party, a trusted third party, which allows you to input data from external services onto the blockchain. So therefore, as the blockchain itself is a closed system, so it cannot, because of its determinism, it cannot access external services. It needs third parties that inputs these data onto the blockchain. And this is something that's somehow a little bit dangerous, because this trusted third party, so to say, represents a single point of failure. So if this entity somehow tries to cheat or just stops working, then your smart contract, which relies on that information, is broken. That's something that's very important here. That's the first point I think that's important about the oracles here. For example, an oracle would be if you would need to For example, if you want to access weather data, so I think I also told this last week, but if you want to, for example, know about the rain in some certain region because you have insured yourself on the blockchain, so there's actually a company which does that, then you need to be able to have a reliable data source for this weather, because otherwise this third party would be able to decide over who gets maybe the insurance money or not. So that's very, very dangerous or very, very error prone. So you have to keep that in mind. B, explain the difference between asynchronous and asynchronous Oracle. I think there is something that's, there is a question about that already on Tweetback. I think that we can cover here in a second. So I'm trying to pull up the slides for the respective what you see here is the synchronous Oracle, and we also have the asynchronous Oracle. And the exercise asks us explain the difference between a synchronous and an asynchronous Oracle. So let's take a look at that. So first of all, I think both of them fulfill the same goal. That's the first important point. We get data from external data sources on-chain to further process them. The only difference between is there's two difference, so to say. So the speed the data is provided in terms of can we use this data instantaneously, in terms of we ask the question and we receive it in that second. Okay, I need to turn out WhatsApp here. Sorry for that. So that's the so to say the quickness. Can I use it instantaneously, or do I say, okay, I'm requesting it and I have some time and I want it back in 2 or 3 blocks or sometime later? That's the first part, and also the second part is the freshness of the data. So how fresh is the data? For we can either say, okay, when we want to instantaneously access data, then it cannot be that fresh because of the synchronous Oracle always writes data for some time, and so after, for example, it writes every 30 blocks the new data on chain, and you access it right after it, then you're lucky. But if you, or for example, after 29 blocks, you're still waiting for the data and you access it, so the data will be 29 blocks old. So that could be the case. But in asynchronous oracles, if you wait some time, then you are really able to get the most accurate and most fresh data here. What important here is, I think, how these two parts work, because there is a significant difference. And I'll try to not to go through these slides, because I think you saw them. I think I'm trying to provide a second way of drawing them. So then I can explain each and every step here, and then you know what's going on. So when we talk about oracles, we have two parties involved always. So we have an externally owned account, maybe something like Blue Eye. This externally owned account is so to say owns a smart contract here. So we have a smart contract, put it away, and this is party one. So this belongs to user A. That's important here. And then second of all, we have another smart contract, and we have also an EOA, an externally owned account, but that's from party B. And you now need to know that party A wants data, and party B, delivers data. So And what you have to think about is that this party B, which delivers data, is actually our Oracle. That's our Oracle service. And our Oracle service is basically an entity, a business, for example, which owns, first of all, the externally owned account with some funds and the smart contract with the details about with the functionality to provide data to some other smart contracts. So let's assume this the case of a synchronous oracle. What happens here is the synchronous oracle here is constantly updated. So this happens every I don't know, every 100 blocks. This smart contract here is updated. That's the important part. So the smart contract is updated with data. And when the externally owned account here needs some data, or wants the smart contract to execute something which requires some data, then you have following process. So we say, okay, we have some kind of execution. We don't actually care what function that is, just that the function requires data from the smart contract, from the Oracle, and calls like give me some data. And this smart contract executes that information, retrieves the information this externally owned account has stored previously in it, and sends back this data. And then the smart contract can do everything it wants with this smart contract here, with this data here. That's the important part here. So keep that in mind. Okay, so that's for the synchronous oracle. So key point, we update every 100 blocks or every n blocks, and the data is instantaneously provided. What is now the difference with an asynchronous oracle? And that's a little bit more complicated and can be moved it away. So an asynchronous oracle is where the oracle is not constantly updating the smart contract. Why? Because there are two reasons for that. First of all, it is very expensive. And second of all, it could be that the data required is the solution space or the data space where a smart contract could require data could be so high that it's completely infeasible to store this data on chain. Let me give you an example. So, for example, in this synchronous oracle, this oracle could always provide the information for the weather of Munich. Could it do? But it would only be relevant for Munich. So maybe we need to be able to decide a little bit on which data we need. So, for example, we do not want it to have a specific location, but we want to have a generic for every location. So what we want to do is we want to provide a coordinate to this oracle and ask the oracle, tell me what the weather is at this coordinate. And the oracle asks its services, its weather information system, and then gives back the data. And if you would store all temperatures for all locations every time in the smart contract, this is definitely infeasible. So that's the point here. If you have data that is very simple, very unique, so to say, and you know that you only need exactly that, then you could use a synchronous oracle. But most of the time, the data requested from smart contracts is more complicated or is more complex, and therefore you need to have a system that allows you to input any data you need. And what happens here is with an asynchronous oracle is a different way, because now we need to be able to have a notification. So for example, we want now also execute some. So we execute something again, and the smart contract now asks, do you have? So do you have this information, or requests an information? So maybe it does not ask. It's not asking, but it's just some kind of a request. And the smart contract itself has not the data. So that's the assumption, the initial assumption that we're doing here. And what happens in this smart contract, it does something that I want to show you code-wise. Where is it? It does something that's this function. It invokes this oracle, and it says invoke oracle. So we could provide some arguments here. So for the sake of simplicity, we omitted the argument here, but you could just say emit oracle invoked msg.sender, and this emits an event. So what is an event? We covered this in the lecture, but I want to mention it briefly. An event is something that is basically like a log. It shows up when you're looking at a smart contract and say, okay, tell me what logs this smart contract has emitted. Then it pops up. We will see later on in the lecture that there is a very easy way to access these logs and to decide on it. So if I see a log that's important for me, then I can say, okay, I'm deciding upon this log that I need to do something. And this is exactly what this Oracle service does, this company. So this company tries to, so this emits something like let's do it like that. So we have a event. And there is a server here. So this Oracle service has some kind of server, and it listens constantly to these events. It says, okay, tell me when an event arrives. Tell me that. So this server is connected to a full node, and this full node tells the server here when a new event arrives. And when a new event arrives, then the server decides, okay, there is someone who needs data. Okay, I'm going to ask some kind of web server. So I don't know, weather.com, I don't care. This data is sent back to the server. And this server now issues a transaction with its own externally owned account to the smart contract alongside the data. And now what you see here is that I use two different colors. I use blue for the maybe I should use another color. Maybe let's do something like yellow. So this is one transaction. So the green one is a transaction. One transaction with a message. So the request in the middle is, so this one, this is this is the message. And what now happens is that this data is basically sent to the smart contract, to this Oracle smart contract, and this Oracle smart contract traces back or sends back, calls the other smart contract with the data. And now the smart contract executes again what it has to execute. So the good part here is that so we have the fresh data, but it's also a little bit more complex to implement, because if you look here, then you see that this callback function needs to call back this Oracle contract and needs to ensure that sufficient gas is provided, that so these oracles have to know each other. So that's very important. So therefore is a address public oracle. So we define it with our constructor, this Oracle smart contract, and with this modifier only oracle, we require that the msg.sender is the oracle. So only the oracle is allowed to execute this callback function. That's a very important point. So these two contracts are very tied closely together. So that's the key part here. That's, I think, the part here. So I think there are questions here on tweetback. So I won't answer any exam questions right now. First question is, could another malicious smart contract emit the event causing the server to write data, although none was requested? So obviously, this is a very simple example of an asynchronous Oracle contract. But you can imagine that we could extend this asynchronous Oracle smart contract to a way in terms of, okay, you need to pay Ether before you use it. You need to you need to provide some data. You need to be registered before you can use it. So that's obviously not part of the smart contract, but obviously you would need to harden this Oracle smart contract such that you would be able to provide data to many people, but also to prevent malicious usage. But that's possible. Does this event, which is basically in a transaction, has to be mined before the server can see it? Very good question. Interestingly enough, no. So the event is part of the transaction, and the event gets emitted the second this transaction is mined into a block. But however, you could take a look at all transactions that are currently in the transaction pool and simulate their execution and see if they emit an event that you are interested in. So you would be able to see that event before it's actually mined if you want to do that. And to even think further about that, you would even be able to answer the request before you would be able to answer the request before it actually arrived in the smart contract. So you would be able to make a synchronous, asynchronous Oracle, and that's actually a paper I'm writing on. So very good idea. How does your drawing relate to the actors in slide 14 of chapter 9? Where are the two EUOs in your picture? Where in the picture is the Oracle contract? So let's take a look at slide 19. Slide 14, I'm sorry. So what we have here is I had a little bit more compact here in my drawing. So we have these three blue parts. So we have an externally owned account and a smart contract. That would suffice my left side, my player A. So if you look here, that's my player A here. And this Oracle contract is this smart contract here. And this externally owned account is in this Oracle service, as I mentioned here. So Oracle service says the Oracle service also needs an externally owned account to write to the smart contract. So that somehow, yeah, that's not super precise. I give it to you, but that's so to say the company that runs the Oracle. And first of all, it needs an externally owned account. It needs a web server that would execute all this data. And an external web API, something like weather.com. Okay. Last question on this topic, then we continue. Why can't the external server just send the data to the smart contract? Why does it have to go through the EOA? So the EOA, the externally owned account, is possessed by the server. So the server has access to the private keys. The server cannot just write data. It needs some form. It needs some vehicle, some transaction, some account that's able to generate a transaction to submit this data to the smart contract. So the server is, so to say, in possession of this externally owned account. Yeah. So I wanted to make it explicit that you don't confuse this, but maybe that confuses you more than I anticipated. Okay. Let's continue here. Let's go back. What are the advantages and disadvantages of oracles? I think that's something I mentioned already beforehand. So the key advantage here is, I think, you get access to external data, which you wouldn't get otherwise. But obviously the disadvantages are costs, speed, freshness of data. I have to actually look into the solution, what I came up with. So exactly as I said. So the synchronous Oracle is easy to use because you can use the data right when you call the function from the Oracle smart contract, but the asynchronous Oracle has this live data. And yeah, and the disadvantage obviously is costly in terms of gas consumption, and you have this dependency on a third party. So yeah, that covers it quite good. And then question D, the provider of a synchronous oracle has a daily budget of $10. Every how many blocks can they update the value of the oracle with this budget? Assume average transaction cost, use current values from Etherscan. So I think that's very interesting, especially in comparison when you look back at 2019. The idea here is that you look at what are the current amount of transactions, daily transactions? What is the current amount of transaction fee that's paid daily? What is the number of blocks that's generated per day? What is the price of Ether? And and these should be sufficient to calculate this on your own. So we can take a look at it. How you would do that. I'll just open some websites here, or only one. We're going to look at Etherscan. The number one website to look at. Well, I don't want to make advertisement here for Etherscan. It's quite good. Maybe not the number one, but it's good. So what we need here is we need to have a look first of all at the price. So $229 here. We have some charts here, I think. Charts and stats. And what you see here is for example, a daily transactions chart. That's something I think very important for now. And we need some kind of transaction fee chart. Network transaction fee chart. That looks also good. So let's take a look at the Ethereum daily transactions, and that's quite high today. So 1,111,318 transactions. And we have some transaction fee chart. So a whopping 3,600 Ether is paid. And you also see these transactions that we mentioned beforehand. So 3,600 Ether, and so there are roughly 6,500 blocks a day. You can look it up, but you can trust me on that one. So let's do a short calculation. The calculation looks it's rather simplistic. So we calculate how much, so what the average transaction fee per day is. So that's very simple. So let's do that on the calculator. So I'm sharing here my screen that you see it. So we have 3,600 Ether times 229. So that's our average transaction fee that we pay, the transaction fee per day, and then we divide it by this 1,111. Let's do it like that. 74 cents per transaction usually. And now you can think of yourself in terms of, okay, we want to spend $10. So if you look at the sheet again, we had said we have this daily budget of $10 and now we can say we wanna this amount, just copy it, say 10 through, thank you very much, and through, I think it was something like that. And then you have 13.5 transactions, which you can do, and then you can think about, okay, so you have 6,500 blocks, and then through 13.5, and you see somehow 481. Every 481's first block, you can now create a new transaction to update your Oracle. And I'll leave you the original calculation that we did 2019 inside the exercise solution, because I think it's very interesting. Now we have 400, so make it around 500. And last year when we did this in May 2019, the answer was, and I'll share it with you. Every 76 block. So this really increased heavily. So the transaction fee increased so much, and the price of the Ether was actually higher than this year. But last year the people paid 360 Ether a whole day, and now they are paying 3,600. So that's increased a lot. So while the transaction amount increased by, I think, 50% or so. But the price basically went tenfold. So that's really heavy. That's really interesting, I think, to take a look at that. Okay. We need to get through this exercise. Okay, no more questions here on tweetback. Okay, so a popular application of smart contracts are voting systems. In this exercise, we investigate such a system, which has a very subtle but common bug. Consider the following smart contract. A lot of lines of code describe the intended basic functionality of this contract. What is the problem with the contract? You can assume that the contract creator is binning and does not end the voting prematurely. If you are having troubles to see the bug, copy the code into Remix IDE and try calling some functions. Which Solidity idiom is commonly used to prevent this error, and rewrite the respective code to make the contract work as intended. How exactly does the idiom prevent the error? Okay, so security questions here. So let's zoom a little bit in there. So I'll walk you through the code, I think line by line. I think that makes the most sense. And then we can take a look at what is exactly wrong and how you would approach such an issue. So we start with the first line, pragma solidity larger than 0.5.1 or smaller than and smaller than 0.6.0. So we define the version for the compiler here. Not too interesting. In line 3, we start the definition of our contract called flawed voting. And we start first of all with the declarations of variables from line 4 to line 7. So first of all, we start with a mapping here from address to an unsigned integer, which is public and which is called remaining votes. So we store for each address, we store an integer variable with remaining votes. So the idea here is that in this in this mapping, you can store like this address has 5 remaining votes. When this is initialized, it is for every address, it's 0. So that's not really to consider the standard value here. And then we start, the second line is here a uint 256, so also an unsigned integer, the largest one, an array, obviously, because of the brackets, and it's a public list of candidates. Then we have an address owner. So we define the owner here so that we can identify him or her. And we have a Boolean value, so a true or false value if the voting has ended or not, and it's set to false at the beginning. We have a modifier, which allows us to easily check within a function if the voting already has happened or not. So the idea here is to require that has happened is not true, so that it's false. So if we only would require has ended, then it would return false, but with the exclamation mark it returns true, and require continues to work, otherwise it would fail and the transaction would abort. And this here is to, so to say, to integrate within the code. So basically this modifier says, okay, this require, we execute this one, and afterwards we execute the code from the function that, for example, here this code is executed afterwards. If we would put this line above the require, it would be executed beforehand. So this is, for example, to establish post or preconditions. We have a constructor here with the amount of candidates, so just an unsigned integer. Again, it's public, but can only be executed once. Then we say the candidate's length, so we define the length of the array with the amount of candidates we have, and the owner is the message sender. So we do not define some names here, but just we say, okay, we say the candidates here, that's just an array, and candidate 1 is known somehow who that is. And in this candidate array, we store, so to say, the votes for this person. We have a function called byVotes, which is public, also payable, so it accepts funds from transactions, and it's not ended, so the modifier applies here. We have a additional require statement. The MSG value needs to be larger than 1 ether. So if you send a transaction to this function, then you need to provide more or equal to 1 ether in payment. Then we have a remaining votes here. So to say, the remaining votes is increased by the MSG.value through 1 to the power of 18. 1 times. So also the exponent here is 18, and that's the amount of zeros we need from Wei. So the amount always is given in Wei, in the smallest currency in Ethereum, just like Satoshi in Bitcoin, and therefore we divide it by this amount to get to ether. And so that seems in terms of, okay, we count for 1 ether, you receive 1 vote. And we return all funds that are not divisible by this number. So the modular operation basically returns the rest of this division here, and it's sent back to this MSG.sender. So it's basically transferred back to the person who sent the transaction. Then we have many functions left. So the function vote here allows us to define a candidate ID and an amount of votes we want to send this to the party. Also, not ended modifier is here. And we have 2 requires here. So first of all, the candidate ID needs to be smaller than the candidate.length. That's the reason because you would otherwise go out of bounds in this array. So assume you have 3 candidates, then the candidates are located at array point 0, array point 1, array point 2. And if you would now be able to, if you would provide a candidate ID that's larger than that, you would basically get an out of bounds error there. So that prevents that you don't do something stupid. And we have a require remaining votes minus amount of votes larger or equal than 0. So the idea here is that the remaining votes you have should be sufficient, so that you do not vote more than you are allowed to vote. So your remaining votes minus the amount of votes needs to be larger than 0. If that's the case, then we have 2 things here happening. We have the remaining votes are subtracted from the amount of votes you are trying to vote, and we increase the vote amount or the vote count for the respective candidate you voted here. We have this function payout votes. It's public and is not ended. So it requires that the remaining votes of the message.sender is larger or equal to the amount. And the MSG sender transfer, so we send this, we send the money back to the party who requires these funds or who requests these funds, and we subtract the remaining votes here. The idea behind this is you buy 10 votes, you want only to vote 5 times, and you want to get back your remaining 5 votes or 5 ether that you paid for. And with this function, you can get a payout very quick. We have a function end voting, also not ended modifier here. And you need to be the owner for that. And you set the has ended to true, so that all these modifiers now stop the execution of these functions. And what you have here is the all the funds on the smart contract. So address this basically refers to the smart contract, and dot balance returns the all the monetary funds located on the smart contract back to the MSG.center, so the owner. Last function there, display balance in ether, very easy. Public view returns an unsigned integer balance, and this is basically returns the balance the smart contract has in ether. That's very easy to say here. So that's the basic functionality. We have a vote contract. You can buy votes. You can do stuff with that. So what is the problem with the contract? You can assume that the contract creator is okay and does not end the voting prematurely. So obviously, for example, this if you would have a rogue owner, the voter could end the voting as soon as someone has paid in there. No one could vote, but the owner would get the money. If you have trouble to see the bug, copy the code into remix ID and try calling some functions. So let's take a look at what the error here is actually. So the error is actually in this vote mechanism, and it's very subtle, but it's there. And the issue is here into line 27. And it's this require statement here. The problem is that we have here unsigned integers. So this remaining votes is an unsigned integer, as you see up here. That's the U256. And the amount of votes is also something that is provided as an unsigned integer. So if you have two unsigned integers and you subtract one from the other, there is no way that the result will be negative. The smallest number an unsigned integer can get is 0. And therefore, this require statement in line 27 always is true. This statement is always true. It cannot get negative. It cannot get wrong. And I'll show it to you so that you see it. Where is my Chrome? So what we have here is we have the Chrome. And let's do a little bit of zooming so that you see what's going on here. And so that's the contract I copied in there. It compiles very nice with some compiler version. That's not too important. And we can deploy the smart contract here. We need to provide an amount of candidates here. And the do we have some else? No, we only have that one. So we say it's 3. And now we have a smart contract where we can say, okay, what are my remaining votes for this address that just created the smart contract, for example, 0. And we could say, okay, we want to buy 3 votes here. And you would see this changed to 3 because we now bought the votes. And we could now say, okay, we want to vote for candidate 1 with 1 vote. So that's also possible. And then you can say, okay, what's with candidate 1 got 1 vote, candidate 0 got 0 votes. So that's possible. That works very well. But the issue is really here in this vote mechanism. And that's very interesting because what you can do here is you can go in this, let's first of all buy more votes. I know you all like to buy votes, so let's do that. 100 ether, I don't have that. Maybe 80 ether. So now we only have 16 ether left. And what we can do here is we can vote here. And that's very interesting because I now can vote for the party 0, for example, and I want to provide 10 votes. And now something magical happens. We can execute this transaction, does not fail, and you can check how many votes this candidate has, 10. But now, due to the nature of this program, we have this remaining votes from our msg.sender is subtracted. So we subtracted 10 from 0 in a non-negative integer. And when we now check the balance vote of this, the remaining votes of this account, then you see it's a very, very large number. And this can actually be used to say, okay, I want to again have the 80 votes that the 80 Ether, the first contract has paid in, to actually get back. So executed very well. And now you see our other contract has cheated its way out of the system here. And yeah, was very successful with that. So that's how it works here. And now let's continue here because now we can think about, okay, the problem, we found it, and now what can we do about it? And I think that's also something that's a very common, unfortunately, in Solidity. And I think I show you a small, we go over the slides so that you see what's going on here, and that you have a very short introduction to the topic. But apart from that, I think that's important here. So let's do this one. I hope you can see it now. That looks good. And what we need here is safe arithmetic. So the problem is Solidity or the Ethereum virtual machine, the Solidity does not provide a internal over or underflow check. So you need to do that yourself. So you need to always check if integer variables overflow or underflow. And you can do this the best with the SafeMod library. And ideally, you implement this contract or you integrate it into your smart contract either by implementing it directly, what a lot of people do, or you are referring to it as a library. And you can use these functions in terms of multiplication, subtraction, and addition. Interestingly enough, you will have a hard time with division and modulo function to under or overflow. So they left it out actually in newer versions of the SafeMod library. So that's the solution, so to say. So use safe arithmetic and be aware that this can happen every time. Okay, very good. I think that's about it here.